Now, usually when people talk about AI writing text, they just jump straight to the massive billion-dollar brains. We are going back to the foundational mechanics. We're looking at the nuts and bolts of how a machine actually guesses the next word. We're talking about n-grams, perplexity, and a concept called smoothing, which sounds like a relentless skincare routine, but is actually the only reason your computer doesn't crash every time you type a creative sentence. It's a really foundational topic, and since we are treating this as a proper educational deep dive, I want to set the syllabus right up front for you. Let's hear it. By the end of this conversation, you, the listener, should be able to do 4 things. First, explain tokenization, which is how a computer slices up language. Second, calculate conceptually, at least, the odds of the next word using n-gram models. Third, understand perplexity, which is how we grade the machine. And finally, the really clever bit, how we solve the zero probability problem using smoothing. Perfect. Let's start at the very beginning. This is our prior knowledge check. Think about how you read. Before a computer can predict the future, it has to be able to read the present. But I assume it doesn't read the way you or I do, scanning the page and imagining a dragon. No, not at all. When we look at a sentence, we see meaning, we see a story. A computer just sees a raw string of characters, just a long list of bytes. So, to make sense of it, it has to chop that string up into bite-sized pieces. We call these pieces tokens. And the process is tokenization. Okay, tokenization. Let's work through an example together. Listeners, picture this phrase in your head. Bilbos, pipe, and tobacco. If I were guessing, I'd say the tokens are just the words. Bilbos, pipe, and tobacco. 4 tokens. That is a very human guess. But a computational linguist, or the NLTK library in Python, which is the standard tool, would actually correct you. It splits that exact phrase into 5 tokens. 5? Wait, where's the 5th one coming from? It splits Bilbo and the apostrophe S. So the list is Bilbo, then apostrophe S as its own separate token, then pipe and tobacco. Okay, so Bilbo is one thing, and the possession, the apostrophe S, is another. Why create that extra step? Let's do a quick formative check-in here. If you're listening, pause and think about why splitting Bilbos into 2 tokens might be better for a computer than keeping it as one. It's a great question to ponder. Think of the semantics. Bilbo is an entity. The apostrophe S is a relationship. It indicates possession. Those are 2 distinct concepts. By splitting them, the computer learns that the apostrophe is a modular piece. It can attach to Gandalf, to Thorin, to Smaug. Ah, I see. If we kept Bilbos as one unique block, the computer would have to learn Bilbos and Gandalfs as totally unrelated words. Precisely. It makes the model so much more flexible. This relies on something called the Pin-tree-bank standard. It uses regular expressions, basically complex search patterns, to handle edge cases and punctuation. Because punctuation isn't just decoration. A period is a token. A comma is a token. They are the traffic signals of the sentence. So, step 1 is chopping the text into this bag of Lego bricks. Tokens. Now, the computer has the pieces, but how does it figure out which brick connects to which? This brings us to the core engine of this deep dive. The n-gram. The n-gram. This is the main tool for what we call word-language modeling. The goal is deceptively simple. Predict the next word given the context, but context is a very heavy word. Yeah. An n-gram model simplifies context by saying, I don't need to know the whole book. I only need to look at the last few words. Let's scaffold this instruction. We'll start simple and get more complex. The text starts with the unigram. Right, the unigram. Uni meaning 1. This is also known as the bag of words model. In this world, the computer assumes that words have absolutely no relationship to each other. It just counts how often they appear in the bucket. So let's look at the math here. If I'm training it on The Hobbit, and the name Bilbo appears, say, 15 times in a text of 1,000 words, then the probability of the next word being Bilbo is simply 15 divided by 1,000. That's 0.015. Okay. The Unigram model thinks Bilbo had a 1.5% chance of popping up at any given moment. Completely. Regardless of what came before it. So it ignores the sentence entirely. Completely. To a unigram model, the sentence, the cat jumped, has the exact same probability as jumped cat the. It is just math based on raw frequency. It's terrible for generating coherent text because it has 0 memory. Okay, so unigrams are a bit distinct from how humans actually speak. Let's upgrade the Bigram. The Bigram. Now we are getting somewhere. This is a first-order Markov model. That sounds fancy, but it basically means I don't care about the ancient history of this paragraph. I only care about the one word that just happened. So it looks at pairs. Yes. Yeah. If we want to know the probability of the word said, we ask, what is the word right before it? If the previous word was Gandalf, we look at our training data and count. How many times did Gandalf appear? And out of those times, how often was the very next word said? So the math is the count of the exact pair Gandalf said divided by the count of just Gandalf. Exactly. We are conditioning the probability on the immediate history. This is infinitely better than a unigram, because said follows Gandalf way more often than said follows to back up. But we can go further, right? A trigram extends the window to 2 previous words. So now we aren't just looking at Gandalf, we're looking at said Gandalf to predict what comes third. The window size is n. As n gets bigger, you capture more context. So a trigram is smarter than a bigram, which brings up an obvious question. If bigger is better, why start there? Why not a 10-gram? Why not look at the last 10 words to be super precise? That is the million-dollar question. And it brings us to the fundamental trade-off of n-gram models. Yes, increasing the window captures more meaning. A 5-gram might capture a whole phrase like, in a hole in the ground. But here is the catch. Data sparsity. Sparsity, meaning we just don't have enough data. Exactly. Think about it. The longer the specific phrase you are looking for, the less likely you are to have seen it in your training book. If you are looking for a specific sequence of 10 words, it might never have appeared in the history of the English language. If the count is 0, your model knows nothing. It's flying blind. So we usually stick to bigrams and trigrams as a compromise between being smart and actually having enough data to count. Okay, hold that thought on the 0 problem, because I know that's a huge part of where we're going with smoothing. But before we try to fix the model, I want to pause for a metacognitive check. We built a model, but how do we even know if it's actually any good? This is crucial. We need a report card. Perplexity is that report card. I love the name. It sounds like exactly what it measures, how confused the computer is. That is basically it. Perplexity is a measure of surprise. If I give the model a test sentence and the model says, oh, naturally, I totally expected those words in that order, then the perplexity is low. The model is confident. But if the model is constantly shocked by the words it sees, wait, Hobbit, I did see that coming. The perplexity is high. The text uses a really good analogy of a die roll to explain the score. Right. Imagine you have to guess the next word. If your model is really good, it feels like rolling a 4-sided die. You have a 1 in 4 chance of getting it right. That corresponds to a perplexity of 4. But if your model is terrible, it's like rolling a 50-sided die. You're just guessing blindly among 50 options. That's a perplexity of 50. So in this game, a low score is the goal. We want the model to narrow down the options. Exactly. We want to minimize uncertainty. There's a mathematical detail here that I want to flag because it shows up in a lot of AI literature. To calculate this, the source says we use log probability instead of just multiplying the regular probabilities. Why logs? Is that just to make it look harder? No, this is a very practical engineering problem. Probabilities are small numbers, like 0.01 or 0.0003. When you calculate the probability of a whole sentence, you have to multiply all those tiny numbers together. And if you multiply 0.01 by 0.0.0, you get 0.0000000. You get a number so microscopic that the computer essentially gives up. It runs out of decimal places and just rounds it down to 0. It's a hardware limitation called numerical underflow. The computer literally cannot handle how small the number is. Exactly. But if we take the logarithm of the probabilities, we turn that multiplication into addition. If you remember your high school algebra, log A times B equals log A plus log B. Summing up negative numbers is stable. The computer can handle it all day long. So mathematically, summing logs is equivalent to multiplying probabilities, but it doesn't crash the calculator. That is a great tip for anyone doing math on a machine. Logs save lives. Okay, so we want low perplexity, and we use logs to keep the math stable. Now let's go back to that crisis you mentioned earlier. The data sparsity problem. The 0 probability trap. Right. This is the fatal flaw of the basic n-gram model. We call it maximum likelihood estimation, or MLE. It relies entirely on what it has seen before. This addresses a common misconception. People think if I feed the computer a whole book, it just knows English. It doesn't. Let's say we are training on The Hobbit. And let's say the specific Bigram Gandalf said never appears in the book. I know, unlikely for Tolkien, but hypothetically. If Gandalf said is not in the training data, the count is 0. And if I ask the model, what is the probability of the sentence Gandalf said to Bilbo? The math involves multiplying the probabilities of each pair. If one of those probabilities is 0, the whole thing becomes 0. Everything is 0. The model declares that the sentence Gandalf said to Bilbo is mathematically impossible. It cannot exist. Which is ridiculous. Just because Tolkien didn't write it doesn't mean it's not valid English. Exactly. This prevents the model from generalizing. It can't handle anything new. So, we need a way to save the model from these zeros. We need to assign some probability to things we haven't seen, just in case. This technique is called smoothing. Smoothing. I like that image. We are taking the rough edges of impossible and smoothing them into, maybe, 3 main ways to do this. Let's walk through them, starting with the simplest. Technique 1, add k smoothing, or add 1 smoothing. This is the blunt instrument approach. You simply pretend that every single possible word pair appeared at least once. You just add 1 to all the counts. Yes. If Gandalf said his account of 0, we force it to be 1. If Bilbo walked his account of 50, we make it 51. Problem solved, right? No more zeros. Technically, yes, the code won't crash, but there's a major disadvantage. It is way too aggressive. Think about how many nonsense word combinations exist. The potato flu. Purple, quiet sleep. Ideas green furiously. Exactly. By adding 1 to all those millions of nonsense combinations, you are shifting a huge amount of probability mass to garbage. You are stealing probability from the real likely phrases and giving it to the nonsense ones. It oversmooths. So the model becomes less accurate because it thinks everything is vaguely possible. It dilutes the truth. Okay, technique number 2. Cats, back off. This one sounds more sophisticated. It is. This was introduced in 1987. The philosophy here is trust your data if you have it. If not, lower your standards. Lower your standards. I relate to that. How does it work mathematically? Let's say we are using a Trigram model. We want to predict the third word based on 2 previous words. If we have seen this Trigram before, great. We use the count. But if the count is 0, we back off to a Bigram. We pretend we only saw 1 previous word and check that count. And if that's 0 too, then we back off to the Unigram. We just check how common the word is generally. That makes intuitive sense. Use the specific context if you can, but don't give up if you can't. The math gets tricky because if you just switch models, the probabilities won't add up to 100%. You have to introduce a discount parameter and a normalizing constant to make the math balance out. But the concept is solid. Prioritize context, but have a fallback plan. But even cats isn't the gold standard. Nezernay smoothing, yes, developed in 1994. Kearney is widely considered the state-of-the-art for n-grams. It introduces a brilliant insight called continuation probability. This is the part that I found fascinating but a little dense in the notes. Let's try a differentiated explanation here. Let's really break this down for the listener. What is the key innovation? Okay, let's look at this carefully. Kneserny realizes that raw frequency isn't the only thing that matters. It matters how many different contexts a word appears in. We call this versatility. Let's use an example often cited in this field. Think of the word Francisco. In a typical corpus, Francisco is actually quite common, but it almost exclusively appears after the word San. Right, San Francisco, it basically has one job. Now compare that to a word like glasses. Glasses might appear just as often as Francisco in total count, but it appears after reading, sun, drinking, broke my wear. So glasses is versatile, it's a social butterfly. Francisco is a one-trick pony. Exactly. Now suppose our model sees a new phrase it doesn't know, let's say, the magical, and we need to guess the next word. A raw frequency model might say Francisco is likely because it's a common word overall. Just looks at the total count. But Kneserny looks at the continuation count. It looks at the history. It sees that Francisco only has one context, and it sees that glasses has many contexts. So it correctly guesses that glasses is more likely to complete a new, unseen phrase than Francisco. That is smart. It measures how likely a word is to continue a phrase, not just how popular it is in isolation. Precisely. It balances the sheer count with the versatility of the word. And empirically, this works the best for handling unknown situations. So we have built our model, we chopped up the text, counted the n-grams, and smoothed out the zeros with Kneserny. Now for the fun part, output of a model trained on the Hobbit. This is our worked example. Yes, the practical application section. They fed the model the prompt, Bilbo, went, and asked it to generate the rest. Okay, I have the output right here. It predicted Bilbo went, thought, said Gandalf. It's poetic in a weird way. It is. Bilbo went, thought, said Gandalf. It captures the flavor of Tolkien. You have the comma usage. You have thought. You have said Gandalf. But grammatically, ideally, it should be Gandalf said, not said Gandalf at the end of a sentence like that. It's mimicking the style without understanding the syntax. And if you look at the perplexity score, it's about 2.25. That's actually quite low, meaning the model was fairly confident in that weird sentence. There's another example, Gandalf, thought. The output was Gandalf thought, I really must keep him, said Bilbo, and then on the floor. And then on the floor, I feel like something dramatic happened there. Maybe a dwarf fell over. But notice something about the text. It says, Gandalf thought, I really must keep him. It's surprisingly coherent. However, the expert notes mention something about stop word removal. Right. In some of these experiments, they remove words like the a is, the stop words. Why remove them? They seem pretty important for grammar. They remove them to reduce semantic noise. Those words are everywhere and don't carry much distinct meaning. Removing them makes the model focus on the meat of the sentence, the nouns and verbs. But as the source notes, it hurts readability. It makes the text sound like a telegram. Or like a caveman speaking Elvish. Bilbo go, Gandalf think. A fair description. They also mention adding explicit start of sentence and end of sentence tokens. The tags are usually an S inside angle brackets. That helps the model understand that sentences have boundaries, so it doesn't just ramble on forever. So we have a working model. It counts, it smooths, it generates semi-coherent Hobbit fanfiction, but we have to be real about its limits. This is not ChatGPT. This is not even close to modern standards. No. The biggest issue is the fixed context window. The N in Ngram. Right. If you're using a trigram, the model can only see the last two words. It cannot look back to the beginning of the paragraph. It has absolutely no idea that the story is about a dragon. So if I wrote, the dragon woke up, he stretched his wings, he was hungry, he wanted to eat a the model just sees eat a guess, and my guess sandwich, it doesn't know dragon was the subject 3 sentences ago. Exactly. It misses long-range dependencies. It has a memory of a goldfish. And it doesn't really understand what a dragon is, does it? That's the semantic blindness. To an n-gram, the dog chased the cat, and the cat chased the dog are just math equations. It doesn't understand that a dog is an animal, or that chasing implies movement, or that usually dogs chase cats. It counts tokens. That is it. And these limitations are exactly why the field moved on. Yes, the sources explicitly state that these flaws led to the evolution of RNNs, recurrent neural networks, and eventually transformers, which are the engines behind the large language models we use today. Those models can pay attention to words far back in the text. They solve the dragon problem. But n-grams were the necessary first step. You have to learn to count before you can write a novel. So let's wrap this up with a summary and think about how we transfer this knowledge. If you're listening, try to mentally fill in the blanks here. We started with raw text and sliced it up. That's tokenization. We calculated the probability of the next word using n-grams. We graded our model using Perplexity, and when we hit the problem of missing data and zeros, we fixed it with smoothing, specifically Naserne. That is a perfect summary. We essentially built a probability machine. It really makes you look at your phone's autocorrect differently. It's not magic, it's just a really well-smoothed probability distribution. And that leads to a final thought I'd like the listener to mull over. We've seen that with enough data and good smoothing, simple counting can generate text that looks like meaningful language, like our Hobbit example. Bilbo went, thought, said Gandalf, right, it looks like it has intent, yeah. But we know it's just statistics. So the question is, when you chat with a modern AI, and it gives you a brilliant, thoughtful answer, how much of that is true understanding, and how much is just a model that has become unimaginably good at smoothing the data? Is there a line between predicting the next word and actually thinking? That is a question that might keep me up tonight. Thank you for walking us through the mechanics of prediction. My pleasure. And thank you for listening to the deep dive. We'll see you next time.